Hi everybody, welcome back. Now we are going to look at the density operator, which is rho of t, and here we are going to define the matrix elements corresponding to the density operator by this equation: rho mn of t equal to 1 by n sigma k equal to 1 to n a km of t a kn conjugate of t. So this is how we define the density operator, or the matrix corresponding to the density operator. We know this n is the total number of systems in the ensemble. Okay, so from this definition we can say rho mn is the ensemble average of the quantity am of t and an of t, okay, which varies from member to member in the ensemble. So rho mn is the ensemble average because here we are taking the summation over all the systems in the ensemble and then dividing by the total number of systems in the ensemble. So we are taking ensemble average of this quantity am of t and an of t. Okay, so this is rho mn of t, and this rho, that will be a square matrix. Okay, rho will be a square matrix that will depend upon the number of orthonormal functions in the basis in the set, okay, for n. Then so that is rho mn, it is of this form. The rho nn is the diagonal element. Okay, it represents the diagonal element of this matrix. So that is given by 1 by n sigma k equal to 1, k equal to 1 to n a kn of t, a kn conjugate of t. Okay, at both places we have n, so that is equal to 1 by n sigma k equal to 1 to n modulus of a kn of t square, because as we multiply a kn of t with conjugate of it, you will get modulus of a kn square. So what is a kn of t square, modulus of a kn t square? It represents the probability for the kth system to be in the state phi n. Okay, this is the original definition of the probability amplitude. A kn of t is the probability amplitude for the state phi n. So modulus a kn of t square represents the probability for the kth system, okay, kth system to be in the state phi n. Okay, so here actually we are summing this quantity over all the systems in the ensemble and dividing by n, the total number of systems in the ensemble. So one can say rho nn represents the probability that a system chosen at random from the ensemble, okay, system chosen at random from the ensemble at time t is found in the state phi n, because we are taking the ensemble average. Okay, so rho nn is this. Now let's see sigma n rho nn. Okay, rho nn represents the diagonal elements. Okay, rho nn. Now what we are going to do is sigma n rho nn. So what that is it is the sum of the diagonal elements, which is called the trace of the matrix. Okay, so we are finding the trace rho nn. So that is 1 by n sigma k equal to 1 to n sigma n this. So sigma n a kn of t modulus square, this is actually equal to 1 because we are adding together the probabilities for the system K to be in the different states. Okay, we are taking summation over n, so this is the sum of the probabilities for the system to be in different states, and that would be naturally 1. And since we are taking summation over n systems, so we will get capital N in the numerator and capital N in the denominator, and you will get 1. So the trace of the density matrix is 1. This is an important result. The trace of the density matrix is 1. Okay. Now we see the equation of motion for the density matrix. Equation of motion. For that we differentiate this rho mn of t with respect to time. Okay, so dot here represents the differentiation with respect to time. So you will have 1 by n, sigma k equal to 1 to n. You will have 2 times because rho mn is this. And here we have 2 functions, 2 amplitudes which are functions of time. So as we differentiate, we have to apply product rule. Okay, so we are applying product rule. So as we apply the product rule, this is, we get a dot kmt, a kn conjugate of t, then a kmt, a dot kn conjugate t. Then we multiply this with ih cut. So we will have ih cut here, and ih cut is written with this, and here ih cut is written with the a dot kn conjugate of t. And then, as we have seen earlier, we can write ih cut a dot km of t as sigma l hml al k of t. Okay, this we have already done. See, ih cut a dot kn of t, that is sigma m hnm akm of t, sigma m hnm akm of t. Okay, that we have already seen from equation 3. So here I can write this as ih cut a dot km of ih cut a dot km of t can be written as sigma l hml. Here we have ih cut a dot kn of t conjugate. Conjugate is there. So that would be minus sigma l hnl conjugate akl of t conjugate. Okay. Why? Because we know if we take conjugate of this thing, we will have minus ih cut a dot conjugate of kn of t sigma m hnm conjugate akm conjugate of t. So we take the conjugate of equation 3, so this will become minus. So as we substitute here, we'll have this minus sign here, and then we are writing this as sigma l is taken as common. Sigma l appears here, here also it appears, so that is taken as common to this expression, and 1 by n sigma k equal to 1 to n is taken inside, and this is taken inside, so that I can write this as rho ln of t. So I can write this as rho ln of t, the matrix element corresponding to the density operator, and this one I can write as rho ml. Okay, so sigma l is there. Okay, sigma l is there, and here I have hml rho ln, and here hnl conjugate rho ml. Now this matrix element hnl conjugate is equal to hln, because our operator, Hamiltonian operator, is a Hermitian operator, and for a Hermitian operator we know conjugate transpose is equal to the same, the conjugate transpose of a matrix is equal to the same matrix, so that is a Hermitian matrix. And since this is a Hermitian operator, the matrix corresponding to corresponding to it will be Hermitian. So we have HNL conjugate equal to HLN. So I am writing here H, instead of HNL conjugate I am writing HLN. So sigma L HML rho LN. So this is a kind of taking product of the two matrices corresponding to H and rho, and here sigma L rho ML HLN, again rho product of rho with the H. So in operator notation I am writing this as H rho minus rho H MN. So IH cut rho dot MN of T is this. So using a commutator notation we have here H rho minus rho H. So this is actually the commutator of H and rho, the notation that we use in quantum mechanics. So IH cut rho dot is equal to the commutation bracket of H and rho. So this is our equation 4, and this is the equation of motion for the density matrix. Now if the given system is known to be in a state of equilibrium, okay, if the system is in a state of equilibrium, then the corresponding ensemble must be stationary. We have the stationary ensemble. That what that means is the rho dot Mn is equal to 0. So for a system in equilibrium, the ensemble will be stationary. So rho dot Mn is equal to 0. So what we have, this thing is 0. So H rho minus rho H, that is equal to 0. Or one can say the commutation bracket of H rho is equal to 0. So what that means is H and rho commute. That is H rho is equal to rho H. Okay. Now for that, the density operator must be, density of rho must be an explicit function of Hamiltonian. If these two operators commute H rho equal to rho H, rho must be an explicit function of the Hamiltonian operator, that is rho equal to rho of H. Also the Hamiltonian must not explicitly depend on time. What that means is H dot is equal to 0. Okay. So if the basis functions, we have taken phi n as the basis functions, if they are the eigenfunctions of the Hamiltonian, then Hmn, that is given by Hmn, we determine using this expression. H is the operator, the matrix element corresponding to that operator is determined by this integral phi m conjugate H phi n d tau. See this H phi n, H when it acts on phi n, it will give you En phi n, our Schrodinger time independent equation. H phi n is equal to En phi n. Okay, so En will come outside. So I will have En delta Mn, because this is an orthonormal set. So integral phi m conjugate phi n, that will be equal to phi m conjugate phi n d tau, that will be equal to delta Mn. So Hmn is En delta Mn. Okay. Since rho commutes with H, rho is commuting with H, we know for a system which is in equilibrium, the corresponding ensemble is stationary. So H commutes with rho, H rho commutation bracket of H rho is equal to 0. Since H and rho commute, phi n would be the eigenfunctions of rho also. So rho will have the same eigenfunctions as that of H. They will have common eigenfunctions. Okay, so in the same fashion as we have written here, in the same fashion I can write rho Mn, the matrix element corresponding to the density operator, as equal to rho n delta Mn. So this representation is called the energy representation. Okay, so we are choosing our eigen for the basis functions Okay, we are choosing the basis functions as the eigenfunctions of the Hamiltonian. So such representations are called energy representation. So in energy representation, as we have seen here, if m and n are different, it will be 0, and it will be non-zero only when m is equal to n. So rho mn is a diagonal matrix. This is a diagonal matrix because its off diagonal elements will be 0. Okay, so in energy representation, the density operator or the matrix corresponding to density operator will be a diagonal matrix. Now in any representation other than the energy representation, suppose that we are not choosing the energy representation, the basis functions are not the eigenfunctions of the Hermitian or the Hamiltonian operator, then the density matrix may or may not be diagonal. Okay, may or may not be diagonal, but it will be symmetric. Rho mn will be always equal to rho nm, because rho mn represents the probability for the system to switch from one state to another. Okay, from state m to state n. Okay, in equilibrium, the tendency of the physical system to switch from one state to another, state m to state n, that must be counterbalanced by an equally strong tendency to switch between the states in the reverse direction. So this is from m to n and this is from n to m. So this must be same in the equilibrium situation. Okay, so this condition of balancing is required or essential for the maintenance of equilibrium distribution within the ensemble. Okay, so this tendency must balance, tendency to switch from m to n, one state to another, that must be exactly balanced by the tendency to switch between the same states in the reverse direction. So in any representation, the density matrix will be symmetric one. Okay, now let's see the expectation value of physical quantity G. The operator corresponding to that is G. So we are finding the expectation value. Expectation value is determined like this: G integral psi k conjugates G psi k ditto. And we are taking this summation over all systems in the ensemble and dividing it by n. So we are actually taking the ensemble average. Okay, so we take the expectation value of a quantity in a given system in the ensemble. This is in given system in the ensemble, and then we sum over all systems in the ensemble and divide it by n. So we are taking the ensemble average, the expectation value of a quantity, mean value of a quantity. So this is 1 by n, sigma k equal to 1 to n. This psi k conjugate I am writing like this: sigma n a k n conjugate a k n conjugate phi n conjugate. This psi k is written as sigma m a k m phi m. Okay, the usual expansion of a wave function in terms of basis functions. So this is 1 by n, sigma k equal to 1 to n. Sigma n, here we have sigma n, here sigma m. So I am writing sigma n comma m. Okay, akm conjugate akn conjugate akm integral phi n conjugate g phi m ditto. And this thing we know what is this. This is the matrix element corresponding to the operator G. So that is written here G n m, and here 1 by n. The other terms are there, G n m. Then this is written as sigma m sigma n. I am taking 1 by n, sigma k equal to 1 to n here, and akn conjugate akm. Okay, now why I am writing like this? Because this is the density matrix. Okay, So I am writing this as rho mn density matrix GNM. So sigma m, rho mn GNM. So this is sigma n rho mn GNM. See this n, this is actually multiplication of the two matrices rho and G. So I can write this as sigma m rho G mm. Okay. So sigma n rho m and GNM, that is the product of the two matrices, so that is written here, and I will get element, and then I am taking summation over m, so that means this is the trace of the product of the two matrices. Okay, so the mean value of G, okay, actually it is then simple average of mean value of G, expectation value of G, that is trace of rho G. Okay, trace of rho G. Then suppose G is a unit operator. If it is a unit operator and its expectation value, that will be 1, mean value will be 1, and here G will be unit vector, so trace rho will be equal to 1. So trace rho is 1. Trace of the matrix corresponding to the operator rho is 1. That we have already seen. Okay, we had already seen that trace is equal to 1 here. Okay, the trace of the density matrix is 1. The same thing can be proved here also. Okay, now suppose that psi k are not normalized. Psi k are not normalized. Here, as we take the expectation value, we have assumed these are normalized. If they are not normalized, we have to write a term in the denominator to normalize it. Okay, so that will be this 1 by n sigma k equal to 1 to n psi k conjugate psi k d tau. Okay, so this thing is what? Trace of rho G that we have seen, and this thing will be trace of rho. Okay, this will be trace of rho. So if the psi k, the original wave functions, are not normalized, the mean value of expectation value of G over the n simple, that will be trace rho G by trace rho. So equations A and B, equations A, this is equation A and this is equation B, they show that expectation value of any physical quantity is independent of the choice of the basis. Okay, the basis does not come here, so it is independent of the choice of the basis.